All right, let's get straight to it. For the better part of a century, physics has been wrestling with a huge problem, a deep crack that runs right down the middle of our understanding of the universe. Today, we're looking at a new model that might just fix that crack by completely changing how we think about gravity. And this isn't just a minor tweak, it's a potential revolution. You know, this ancient idea really gets to the heart of it. Our universe works because of a few fundamental forces: electromagnetism, the nuclear forces, and gravity. They run the whole show, from atoms to galaxies. But what if one of these isn't like the others? What if gravity has been hiding its true identity from us this whole time? So here's the core claim, and it's a big one. Gravity is not a fundamental force. Instead, this framework says it's a composite effect, something that emerges on the large scale from the combined energy of all the other forces.
To get why this is so important, you have to appreciate the central problem we're facing. We basically have two masterpieces of human intellect: general relativity, our guide to the big stuff like stars and galaxies, and quantum field theory, our rulebook for the tiny world of particles.
And here's the problem. These two theories are completely, fundamentally at odds. General relativity paints a picture of a smooth, elegant, geometric spacetime that bends and curves. Quantum field theory, on the other hand, describes a jittery, chaotic world of quantized fields buzzing with energy. They don't just disagree, they speak entirely different languages. This new model, though, it might just be the Rosetta Stone we've been searching for.
So what's the new mechanism here? The idea is that what we call gravity is just the macroscopic, geometric result of adding up all the energy from the electromagnetic, strong, and weak nuclear fields. Gravity isn't a standalone player. It's the final score of the whole team's effort.
So how do we get there logically? Let's walk through it. It all starts with Einstein's field equation, the classic. Now that stress-energy tensor on the right side, just think of it as a complete inventory of everything that can bend spacetime. Mass, energy, pressure, the works. The key insight is step 2. We unpack that inventory into its separate parts: energy from mass, energy from electromagnetism, and so on. And here's the beautiful part. By the time you get to the end, all that mind-bendingly complex math simplifies. It turns into a simple sum of all the different energy densities. That right there is the big conceptual jump.
And this is the punchline. Gravity isn't some extra force. It's just what spacetime does when you pack it with energy from all the other fields. Now, this isn't the first time an idea like this has been floated. Andrei Sakharov had a concept of induced gravity years ago, but his idea was more about spacetime pushing back against quantum fluctuations. This model is much more direct. It says you can literally calculate gravity by adding up the energy you find in a given volume of space. It's an accounting principle.
And this whole idea, this whole conceptual leap, gets boiled down into a single, new equation. It's designed to bring all these different energy sources together under one gravitational roof.
And here it is, the composite gravity equation. It looks a bit intense, but what it's doing is actually pretty straightforward. It's calculating the gravitational pull at some point by adding up or integrating all the energy densities from mass, from electromagnetism, and from the strong and weak forces over a certain volume of space. It's a full audit of all the energy on the books. So, what exactly are we adding up? Well, it's the usual cast of characters from modern physics. You've got mass energy, that's your classic E equals mc squared. Then you've got the energy stored in electric and magnetic fields. You also add in the immense energy from the gluon fields that hold atomic nuclei together. And finally, the energy from the W and Z bosons of the weak force. Now, here's where it gets really, really interesting. See those Greek letters, alpha, beta, and gamma? Think of them as weighting dials on a cosmic mixing board. We don't know their values yet, but they tell us how much each type of energy gets to contribute to the final gravitational effect. Figuring out what these numbers are is the next great experimental quest. And this is absolutely crucial. This model doesn't throw out a century of brilliant physics. If you turn those new dials, alpha, beta, and gamma, all the way down to 0, the equation collapses back into standard general relativity. It's a perfect match. So this isn't a replacement for Einstein. It's an extension meant to cover the areas where we know GR is incomplete. Which, of course, brings us to the most exciting question of all. Where does this new model predict something different from general relativity? Where can we actually put it to the test? This right here is the most radical prediction. The model says you can have gravity without any mass. If you can create a region of space with an insane amount of electromagnetic energy, for example, but no actual matter, that spot should still bend spacetime. And that gives us a fantastic, clear-cut test. Imagine a plasma made of pure light, a cloud of photons, with no particles. According to general relativity, on the left, that should generate next to no gravity. But this new composite model on the right predicts a significant gravitational field created solely from the energy of the light itself. That's a black and white difference we can actually look for.
And this isn't just a lab experiment. The model predicts we'll see these effects differently in various cosmic settings. In a pulsar binary, for instance, where magnetic fields are king, the trigger point for seeing these new effects would be totally different than in simulations of the early universe, which was just a hot soup of all energies. It gives astronomers different targets to aim their telescopes at. This could even help us solve some of the biggest mysteries out there. Think about dark energy. What if it isn't some weird, exotic new substance at all? What if it's just the background gravitational effect of the weak nuclear field's energy spread out over the vastness of space? This model puts that possibility right on the table. So what's next? The best part about this framework is that it isn't just a thought experiment. It lays out a clear, actionable roadmap for the entire physics community to either prove it right or prove it wrong. And here's that roadmap. First, we need to build better computer simulations of extreme places like magnetars to predict exactly what signals we should be looking for. Second, we need to dive back into the theory and see if we can derive those weighting coefficients from first principles. And third, we need to design real-world experiments, probably using high-intensity lasers, to try and create and measure gravity from pure field energy.
When you boil it all down, the entire experimental chase comes down to finding these 4 numbers. We need to measure alpha, beta, gamma, and K. These values are the key. Once we have them, we'll know if we found a new picture of the universe or if it's back to the drawing board.
Because in the end, the ultimate prize here is unification. By redefining gravity as an emergent effect of the other fields, we fundamentally change its relationship with quantum mechanics. Suddenly, they both have a common currency: energy density, and that might be the very foundation for the bridge we've been trying to build for decades between the quantum world and the cosmos. Which leaves us with one final fascinating thought. For hundreds of years, we've thought of gravity as a solo act, a single dominant force shaping the universe. But what if we've had it all wrong? What if gravity isn't a single force at all, but the universe's ultimate team effort?